Okay, continuing on with orthogonality, I'll throw a theorem at you here. I think this is theorem 3. The columns of an m by n matrix Q form an orthonormal set if and only if Q transpose times Q is the identity matrix in terms of n. And let's make sure this multiplication is correct. So Q is m by n, which means Q transpose is n by m. So this is n by n times m by n, and that's n by n. So yeah, that makes sense. Okay. And so this gives us a way to define what's called an orthogonal matrix, right? So an n by n matrix M whose columns form an orthonormal set is called an orthogonal matrix. And these arrive all over the shop, especially in applications. And so this leads to another theorem, theorem 4. A square matrix M is orthogonal if and only if Q inverse equals the transpose. This is huge. Okay. All right, so let's do an example here. This is a tough one, so we're gonna really suss this out here. So we have A is the matrix 0, 1, 0, 0, 0, 1, 1, 0, 0. And you may recognize this as these are the standard basis vectors. So this is E3, E1, E2, and that becomes important in a minute, the ordering. Okay. Now, what we want to show is that A is orthogonal and find its inverse. And by theorem 4, if A is orthogonal, then its inverse is equal to its transpose. Right? So if we show that A is orthogonal, we don't actually have to compute its inverse, which we found out earlier in this course and in the past is something you always want to avoid. So this orthogonality is great because it gives us a way to find inverses without actually finding inverses. You get them for free just by swapping the rows with the columns. So let's show that A is orthogonal. Okay, well, we're going to go through all these steps, but for A to be orthogonal, what do we have to show? Let me get my thing here. Make sure I've got everything sorted. The columns need to form an orthonormal set. So we need to show that 1, the columns of A are orthogonal, and 2, that each vector or each column has length 1. Okay. Well, there's only one entry in each column, and it's 1, so This guy's checked out without any work. It's trivial. We need to show the columns of A are orthogonal. And so I'll call these A1, A2, and A3. And sure enough, A1 ought A2 is 0. A2 dot A3 is 0. And A1 dot A3 is 0. Okay. So these three columns form an orthonormal set, and therefore A is orthogonal. Okay, so A inverse, by this theorem, equals A transpose, which turns out to be 0, 1, 0. Oops, I don't want that. So let's see, it's well, I erased the wrong piece. Hold on. There we go. Back to black. It turns out to be 0, 1, 0, 0, 0, 1, 1, 0, 0. And so that's A transpose, and that equals A inverse by the theorem above. It's kind of a trivial example, and so let's look at another one here. Let's let B be this rotation matrix. Cosine theta, sine theta, minus sine theta, cosine theta, right? And again, we're supposed to show B is orthogonal and find B inverse, right? Which is going to be equal to B transpose. All right, so to show orthogonality, we have to show one, the columns of B are orthogonal, and that 2 each column has length equaling 1. Okay, so let's see here. Column 1. So the length of column 1 is going to be the square root of cosine squared theta plus sine squared theta, which is 1. And the length of column 2 is the square root of minus sine theta squared plus cosine squared theta, which is also 1. So we've shown that each column has length 1, so they're unit vectors for any angle theta, including 0. And so now we want to show that show orthogonality. Okay. So what do? We take column 1 and dot it with column 2, which is cosine theta minus sine theta plus sine theta cosine theta, and that equals 0. Okay, so they're orthogonal, and therefore this matrix, this rotation matrix, is an orthogonal matrix. Okay, so this matrix A above, some note. Matrix A is called a permutation matrix. Because since it permutes the columns of the identity matrix. And this is known as an isometry. as an isometry in geometry, which we'll talk about at length later on in the course, but this is sort of the first place where you see it. And so the last theorem, we're just going to tie a bunch of stuff together here. What are we up to? Theorem 5? Okay. So let M be an orthogonal matrix. So A. M inverse is orthogonal. Okay. B. The determinant of n is m is plus or minus 1. C. If lambda is an eigenvalue of m, then the absolute value of lambda equals 1. And D, if m1 and m2 are orthogonal, then so is m1 times m2. Okay, and keep in mind that this, so note, if lambda is a complex number, this holds. So this holds in the complex numbers. All right, well, this last theorem, I might ask you to prove part of it in the exercises. Proof is less to the student, but you'll use this for some of the problems. And I think there's a fact that some of you used in the last homework that you knew nothing about. You just picked it up from whatever internet crap you got and didn't realize that. And this is a massive fact. So we're going to say, let M be a square matrix, right? And assume A is invertible, okay? Then, here, let me make this even better. Okay, better. Come back. There we go. So let A be a square matrix and assume A is invertible. Let lambda 1 be down to lambda m be the eigenvalues of A. Okay. The determinant of A is lambda 1 times lambda 2 times the product of the eigenvalues. Right? So for example, if I gave you the matrix 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 0, 0, 1, 2, 3, 4, 0, 0, 0, 1, 2, 3, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, which is what, 6 by 6, and said, what are the eigenvalues of A? Well, they're 1, 1, 1, 1, 1, 1. So the algebraic multiplicity of lambda equaling 1 was 1. And what's the determinant of A? It's 1. Because 1 times itself 6 times is 1. All right, now you'll have enough to do the homework. Fun.